All right. Sorry, I'm starting up a bit late today, but we're getting back on the Advent of Code train. Jumping back into problem 14, where we previously had to work out how grains of sand sort of arranged themselves. And actually jump in here. And last time we just kind of read and started thinking about part 2. And the point is basically, instead of the sand falling into kind of the abyss, I think they called it, the sand instead hits a floor that is 2 units below the lowest unit on in the grid, the lowest rock in the grid. So we'll have to find the lowest rock in the grid, figure out where the floor is, and then we just let the sand pile up, and we ask how many units of sand does it take before we block the entry point from the falling sand. So last time, just at the very end, we implemented this function that gets us the lowest y. So now the floor is going to go in 2 below that, and we were thinking about basically how to model the floor. And there are a couple different options. One is that we could actually draw, we could work out bounds for how far the sand can go to either side. So like without an obstruction, the sand would make a triangle. And so we know how far to either side the sand would go. And so that's how far we would have to draw the floor if we just want to do it with by drawing rock. Another way we could do it is to update the get next sand position to have a floor. Which I think I like better, because it means we don't have to waste space kind of filling in the floor. So I think what we'll do is we'll turn the get next sand position. We will have a floor y, which will be an option. I32 is fine. And what to say here. So we already are returning when there's when we hit the when sand hits the starting position. But yeah, okay. So the only time that sand can hit the starting position is if yeah, I guess we need to return from here also. So this is gonna have to say it's interesting, actually. So it's going to pile up, and then no, it should be fine. So this should finish, like there should be an iteration of drop sand that drops from the starting position when there is a floor below, when there are 3 grains of sand immediately below the entry. Then it will add the sand, and then the next time that this runs, it should just hit this condition and return immediately, which is fine. So then in here we just need to handle the case of the floor. And so let's do that by saying the floor is at y. And let's actually, we can move this stuff down. And the idea is going to be that if we're above the floor, then we're automatically at rest. And we just return. So let's say if let's match floor y. If it's none, then we do nothing. If it's sum y, then we do if y minus 1 is v dot y, then we return sum v, right? Because we've definitely landed, and this is minus 1 because y minus 1 is the space above the floor. Okay. And then, okay, so now we have a bunch of call sites that obviously aren't working. So it occurs to me we actually don't need to pass this in. Let's actually not pass this in. Let's make it a member. Let's say match self dot floor y, and then what we'll do is the cave can have a floor y option I32, and we'll just pass that into the constructor. And then from strings, we're going to have to tell it where the floor should be, if at all. So we can say floor delta y, and we'll make that an option I32. So it'd be plus 2 in our case in particular. And then from lowest points, we can see here, get lowest y. Instead of doing it this way, let's let's actually just copy this up and do it in here. Whoa, what just happened? Okay. So let's say let lowest point be, and it won't be self, it'll just be lowest points. And then let floor y be match floor delta y. We don't even have to do that actually. We can just say let floor y be floor delta y dot. So I want to keep nuns, but I want to map the contained value by saying this is delta y, and so we want lowest point plus delta y, and then we say floor y, and let's option of I32. This should be an option of I32. Okay. Cool. So now that figures out the floor. And what else we got? Let's get rid of this altogether. And where are my arrows? From string. So this will just be none. And this will be none. Okay. And then I guess there's something near the top also. Yeah. From strings, none. But then we will have then we can just take this exact same function and toss it down here. And we just say option, whoops, not option, sum 2. So it's going to be 2 lower. Drop sand until abyss should be fine because it should never hit the abyss. So maybe here we'll just say asserts cave dot has hit abyss is false. And okay, things are compiling. Cargo test. And we got a failure, and it has hit the abyss. Okay. But I think the reason for that drop sand until abyss while has hit abyss. Yeah, that's not really what we want anymore, I don't think. Wait, how is it ever hitting the abyss? Oh. No, it's just whenever this returns none, which is self.inAbyss, which is, okay, we've gone below the lowest point, but that's not quite going to do it. We would want to say match self dot floor y none, then do nothing, but sum y, then we say v dot y is greater than y. It has to be below the floor, which should never happen. So we'll just return this. I think I have to wrap this. Okay. And what's the issue here? Oh, that's not a reference. Okay. Where did my... Okay. Okay, stuff is running. I'm just gonna hang forever though. So the trouble now is that this never returns true, which means our loop runs forever. So that can't quite be right. So let's retitle this has hit abyss, or well, do we want to add another flag? Let's just add another flag. That's probably nicer. Has blocked starting point. This will be false. And then in this case, we say self.has blocked starting point is true. And now this can be while not this or self has blocked starting point. And we get a failure. That looks pretty good. So test problem 14b fails. We didn't do the example input for this, which we should do. And what is the answer given to us? 93 units of sand. And it needs to be 14b. Oops. Okay, we're getting 31 instead of 19. Okay. Interesting. So we expect the answer to be the same 2 units lower. So if we run this 24 times, we expect all the sand to be in the same place. Right, so we could, like, in particular, we could take these two. Take this and say, test that simulates sand drops with floor. And now we just say sum 2 here. And this should still be correct. This should pass. It fails. Not only does it fail, it fails immediately. Okay. Let's go ahead and drill into this. That wasn't what I wanted to do. Drop sand, immediately returns. How is that possible? How is that possible? Breakpoints behave really strangely in VS Code. I do not understand how the Rust breakpoints work a lot of the time, I have to say. Okay, so certainly we don't expect that to be true. We expect next stand position to be one below 500 so 501. And the answer we get is 501. So now we expect to go all the way down to 508 or something. Hmm. 505. Cave. Material map. Has one bit of sand in it. It's at 500, 5. Should be at 508. Curious. And I haven't changed any of the inputs. Zero, 1, 2, 3, 4, 5, 6, 8. Yeah, that's right. So why we're coming here? What is self dot floor y? Sum 6. That's wrong. Okay, well that explains it. Why is it sum 6? From strings, we take our lowest points. We need the max, not the min. It. All right, cool. So that passed our example. I was thinking there might be a one-off error potentially with whether or not there's actually a grain of sand at the starting point, but apparently there's not, or this would fail. So we think the answer is 239921. 23921, and let's see if we're right. Boom. All right, problem 14 complete. We continue. Like this, we're getting a little river. We're getting a waterfall. We're getting a waterfall next. Very cool. Beacon exclusion zone. You feel the ground rumble again as the distress signal leads you to a large network of subterranean tunnels. You don't have time to search them all, but you don't need to. Your pack contains a set of deployable sensors that you imagine were originally built to locate lost elves. The sensors aren't very powerful, but that's okay. Your handheld device indicates that you're close enough to the source of the distress signal to use them. You pull the emergency sensor system out of your pack, hit the big button on top, and the sensors zoom off down the tunnels. Once the sensor finds a spot it thinks will give a good reading, it attaches itself to a hard surface and begins monitoring for the nearest signal source beacon. Sensors and beacons always exist at integer coordinates. Each sensor knows its own position and can determine the position of a beacon precisely. However, sensors can only lock onto the one beacon closest to the sensor as measured by the Manhattan distance. There's never a tie where two beacons are the same distance to a sensor. Alright? Manhattan distance is the L1 distance. We've used that before. It doesn't take long for the sensors to report back their positions and the closest beacons your puzzle input, for example. Sure. So consider the sensor at 218. The closest beacon to it is at yep. Drawing sensors as S and beacons at B. The arrangement of sensors and beacons looks like this. Sure. This isn't necessarily a comprehensive map of all beacons in the area, though, because each sensor only identifies its closest beacon. If a sensor detects a beacon, you know there could be no other beacons that close or closer to the sensor. There could still be beacons that just happen to not be the closest beacon to any sensor. Consider the sensor at 8.7. That's what a circle looks like if you do it with respect to a L1 norm. The sensor's closest beacon is at 210, so you know there are no beacons that close or closer. Sure. None of the detected beacons seem to be producing the distress signal, so you'll need to work out where the distress beacon is by working out where it isn't. For now, keep things simple by counting the positions where a beacon cannot possibly be along just a single row. So suppose you have an arrangement of beacons and sensors, like in the example above, and just in the row where y equals 10, you'd like to count the number of positions a beacon cannot possibly exist. Coverage from all sensors near that row looks like this. In this example, in the row where y equals 10, there are 26 positions where a beacon can't be present. Calculated based on the report for y equals 2 million. Okay. Small puzzle input. Let's check it out. Lost my repo here. Okay. Input 15. And now problem 15. And let's get rid of the shortened input stuff. And example input. Yeah, we have a nice little example input. Actually, it's a big example input. But okay. I guess let's throw this into its own input example input 15.txt. And okay. So problem 15, this is really just going to be example input is input parser new. It's just going to be not that either. And example input 15. And okay. And then we want to assert that the problem called on example input results in 26. Okay. So this whole thing where we're only counting one row seems really parochial, like really specific. Which obviously we'll do to get the puzzle answer, but I don't really know why I'm not just computing this for everywhere. It's like my instinct here is just to take the entire space. Oh, I guess I don't know what the entire space is part of the problem. Because they haven't actually told us what the width is, which is fine, because we're counting all the places that a beacon can't be present. So and let's take a look at our puzzle input. Closest beacon is at. These are really small numbers. It's at 13.2 and at 15.3. There's no. Oh, this is the example. Okay, these are big numbers. Okay, so I'm guessing that the point here is that the radiuses of these are kind of big, and so if we try to just go and create a 2 million by 2 million grid and populate everything, it's going to be difficult. So probably what we want to do is be able to query. We want to parse out all the different sensors. And then query the sensors. There are only 19 of them for each point. I guess we'll need to query them for the min and max x. Which is easy enough to do. And then we just count up the points. So I think this question basically comes down to modeling a sensor nicely, which is fine with me. So let's model a sensor. So test sensors. Sensor or beacon? Sensors. Sensors query, and we'll just let sensors be sensor from strings, get example input, which that'll be our parsing, and let's actually go ahead and make this a function because I'm going to call it a bunch of times. So function get example input of nothing returns a vec of string. And it's just that, and then And we'll end up doing the same thing there. Okay. So sensors should be able to parse themselves. Let's just very quickly assert that we get the right number. Should be, was it 19? 14. So 14. And then we can say assert sensor 0 dot beacon is possible at some position. Let's just grab it from the example, perhaps. Beacon 0, 218. Okay, that's the first one. Consider the sensor at 8.7 is the puzzle. All right, let's use the beacon at 8.7, which is 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6. It's the sixth one. And there are no beacons within within a bunch of spaces. So let's say beacon is not possible at 8,7. It's not possible at 8,8. 7,7, or where else? 0.7, or -2, -2. It is possible, though, at a lot of nearby coordinates. -3, -2, -2, -3, and so on. And let's say, is that 7,0 or 0,7? Actually, in fact, -1,7. Still doesn't work. And then we'll do -1, -2,7 is possible. Okay. And I mean, basically, if this is working, then it's just a matter of setting up, useful predicates to count up what we want. So I don't think we need too much more than this, to be honest. So let's go ahead and implement it. Struct sensor. And this will have a position, which will be a vec2, and a beacon position, which will be a vec2. Sensor, function new, position vec2, beacon position 2 returns a self, just position and beacon position. So we're going to need from strings and what else are we going to need? We're going to need is beacon is possible. Position vec2 bool. And this is going to be I mean, I wonder if we don't even carry around the beacon so much as we carry around the distance. Let's do that. Max beacon distance, and this will just be a U32. I'll call this max beacon distance U32. Beacon distance. And then this is very simply self.position. So it's vec2 L1 norm. Oh, it takes a self. Okay, so it's position minus self.position. Get L1 norm is less than or equal to max beacon distance. And if it's less than or equal to it, then it's not possible. So it has to be farther. And this needs to take self. And this needs to be self dot. Okay. So that'll tell us whether there can possibly be a beacon there. And so then we just need to actually parse the strings into the right format. And what do the strings look like? They look like this. Do we want to use the parser for this? Yeah, why not? Just to have it around, let's comment that out, and we'll say parser equal, oops, let parser be parser new. We just want this to be strings into iter map s self from string s collect. String and returns a self. So we instantiate a parser with the string. And we say it's got to be mute. And we say parser dot expect sensor at x equals. I forget, does this panic or does this? Okay, this returns the string, so let sensor header, which we're never really going to use, be that, and we'll expect it, and then we'll just unwrap if it doesn't work, because we've decided we don't mind if things panic. And then we want to parse the value out, so let x be parser dot consume into white space dot. Can this return anything other than dot parse into a I32 dot expect x should be parsable, and then there's a comma space, so let comma space be parser dot expect comma space y equals and I guess we can say comma space y equals, really doesn't matter, but just to have some nice labels, let y be parser dot consume until c equals colon dot parse I32 dot expect y should be parsable. This needs to be a reference, and okay, so then let closest beacon header be parser dot expect space closest beacon is at x equals, and let's go ahead and move this so there's no end of the line there, so we would need, so it can either be a colon or it can be the end of the line, which is just C is this, presumably. And let's throw these into a function. Function parse string to vec2. And I mean, we could put this in vec2, but I don't know, it's a little bit parochial. XY, and we will return vec2 new XY. Okay. Ooh. Yeah, this actually needs to be a mutable reference to the parser. This, or is expected bool found nothing. Yep, sure did. Okay. So now this becomes let's sensor position be self string to vec2 parser. And let's actually call this parse vec2. So I could sensor position and then let beacon position actually think I'm going to get rid of these. And then have something in here that's like x equals, and this will be x equals. Okay, so that gets us our two vectors. And then we want to say let max distance be sensor position minus beacon position dot L1 norm. And we return a new self, which takes sensor position and max distance. Okay. Cool stuff. Okay, so what else to say here? I mean, basically now everything goes into the actual solution here. So this is going to be let sensors be sensor from strings input, and then we want to get we want to get the bounds that we care about. So let's have a couple of functions, helper functions in here that are just like get x bounds. And this will just be a pair of x values. Which are self.position.x minus self.max beacon distance. And self.position x plus max beacon distance. And it doesn't like me because this is a U32. So we can just say as I32. And this is going to be essentially the same thing. And so now we can say let min x max x be sensors, iterate over the sensors, map the sensor, get max x bounds, and then we always know the left one is going to be greater than the right one, so we can just then map this and say left, right, and oops, this got away from me a little bit there, and we'll collect at the end of this. I guess we want to fold or reduce reduce, and trying to think if maybe, yeah, this should be fine. But reduce takes two tuples. One is the accumulator, one is the element, and then what to say here? We'll say let L R be element, accumulator dot 0 is if L is less than accumulator dot 0 L else accumulator dot 0, and same thing for R, right? And then we say accumulator, well, we just say accumulator. And reduce takes two distinct arguments. Yeah, I always forget which ones are tuples and which ones are two arguments, but okay. So this returns an option in the event that it has no elements, but it'll always have some elements. But I don't need to collect at the end of this. We can say expect there's at least one sensor. And okay, that worked. So that gets us the min and the max, and then we say what min x dot dot equals max x into iter, and what to do here. We want to filter out only the ones that, so we're going to filter x, and it'll be sensors dot iter dot all sensor sensor dot beacon is possible. X or vec2 new x 2 million. That's the filter, and then we collect, or honestly we can just count. Okay. X here is borrowed, needs to be referenced. And what's the problem? Expected U size. Didn't I? Okay. And let's fix our parens. what's the issue here? Accumulator isn't mutable. Of course, we need it to be mutable. Okay. So the main thing I'm not so sure about here is, so we're going through each element that we need to go through. And then we're bumping that up against every single beacon. There are only 19 beacons. But I don't know, this feels like it could end up being a little slow, but we will optimize if we find we need to. So, sensor, can't find value. These all need to be sensors. Okay, things are compiling. And how do we do? Problem 15b not implemented. Okay, we got a parser error. I assume we got a parser error on the small test too. Yep. Okay. Let's just do this in the debugger. It's going to be simpler, I believe. Okay. Sensor header, sensor position. Oh, bails on me, sure. Oops, I just did it again. Okay, parser. Okay, so we need to be inside parse vec. And now x equals works, and the parser has the pointer is at 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's consuming till white space, but that's wrong. It needs to consume until it hits a comma. So let's go consume until, and C is a comma. Expected x equals, but got space x. Sensor at. Okay. Parse until. Maybe it doesn't. No, it should consume. Closest beacon is at space. Seems right. And surely expect consumes all the way through the space. Confused. X equals is correct. X gets optimized away, but okay, X is 2, Y is something else. It's not going to tell me, that's fine though. And the second time through is where it yells. So it's working the first time. Closest beacon is at space. Really seems analogous. How can it be that when we expect here it works fine, when we expect here it doesn't? Wait. No, because it's not yelling here. One question though is how are we not... Oh, I guess we can consume until... Wouldn't we expect this? That's gonna be unhappy with me. Okay, that's real value. Interesting error message. I'd have expected this line to fail. Anyway. Okay, so we're getting proper failures now, which is good. -2 is not in there. So -2 should not be possible, is if I'm reading this correctly. -2 -2. Oh, I'm not reading this correctly. This is 8. This is -2. And then this is -2. 8. -2, or -3, 8, -2, 9, -2, 7 is fine. -2, 8. This is 10, 9, 8. -2. It's the other way around, right? It's 8, minus 2. Minus 2. And this is let's do 9 minus 2. Let's do 7 minus 2. And let's do 8 minus 1. Eight minus 3. Okay. And not implemented. 12 versus 26. Okay. So we're getting an answer. It is not the right answer. Great. It's not the right answer because the row is different. Okay. This is a row 10. Is that right? Consider just at y equals 10. And then we'll make this one at 2 million. And is that actually where I'm being asked for it? Yes, at 2 million. And this now gets row y, y32. And we will say row. Okay, still not doing it. Still not doing it. So. This needs to be greater than. So the accumulator takes L. If L is less than itself, it takes R otherwise. That makes sense. Filter the beacon, and then we're looking for where the beacon is not possible, right? 26, where it cannot be present. Zero. Any? So we want to filter only the ones such that the beacon is not possible. So that means that for each of these positions, we're looking for any beacon not possible. Yay, logic. Okay. Now we're just off by 1. Does it count? I assume I'm not meant to count the beacon itself. So this is 4 plus all the numbers from 3 to 24. All the numbers from 3 to 24 is 24 minus 3 plus 1. 22, so 22, 26, yeah, okay. So beacon is possible needs to be if position equals self.position, return false. Oh, weird. That was always true. I guess we need to just filter out all the points where there are beacons. Dot filter. Any beacon is possible, or so beacon's not possible. We need to filter out, so we need to not include X if it's equal to the sensor. Means we have to loop through these again, which is fine, I guess. Dot filter X sensors dot iter all sensor dot position dot X is not equal to X. And no, its position is not equal to back new X row line. Like doing 2 passes on this is definitely not the fastest thing, but still. So we take all of the X's, we say, look if any of the sensors is equal, filter it out. So all of the sensors are not equal, keep it in. And then we say, of those, of the non-sensor points, we want to find out if the beacon is impossible with respect to any of the sensors. Which seems fair. So let's say impossible positions. Let's collect it. not getting dupes, right? And then we'll return impossible positions.length. And I want to see what impossible conditions is equal to. Sensors. Length return 27, sure. But I want impossible positions. Which apparently you're not going to give me. -8, -8. 28 and -8 seem like the right things. 28's out here somewhere, -8. 26, negative. Over the whole thing. It's logical. Why can't I see impossible positions here? There we go. Possible positions. So it thinks that -2 is impossible, which I agree with. -2, -1, 0, 1, 2, 3. 2 is still showing up. 2 shouldn't be showing up. It should have been filtered out. Why wasn't it? We are filtering to only x's such that all of their positions... Oh wait, it's a beacon that's there? It's a beacon that's there, not a sensor. That's actually annoying. That's just annoying. Okay, so I assume I don't want to do this, but I do want to say that if there is a beacon there, then it's possible. Okay. So I guess we go back to our previous thing where we say beacon position vec2. We can say beacon position vec2 and let max beacon distance be position minus beacon position, get L1 norm, beacon position, and then if the beacon is possible, we should say if position is beacon position self dot And so now, if any of them say that the beacon's not possible, well, nothing can say that the beacon isn't possible because the sensor responsible for that, for if we hit an actual beacon, the sensor who's responsible for that beacon is the only sensor that can see it by hypothesis. And so now the beacon should be possible there, and it won't trigger, I believe. All right, spent some time thinking that time. And we got a number. 4811 413. Let's check that out. Hey, Mr. Dex, how's it going? Print them out? Yeah, I could. I could have, but I don't know. If the debugger, I'm not wild about VS Code's debugger. At least when it comes to Rust, it just doesn't seem to do a very good job. But I would like it to work well, and so I keep trying to get it to work well. I should probably just work out how to use the debugger a little better. Anyway, I think we got an answer. So let's see here. Drop this in my test. There's also weird stuff with Vim where Vim doesn't want to paste. So I just copied something and it's in my star register. So there we go. Okay, let's see if we got the right answer. Parenthesis. Boom. That's the right answer. 1 gold star closer. Cool. I'm going to read through this, and then, unless it's pretty easy, I need to run, so I'll probably call it there, but let's read through it first. So part 2, your handheld device indicates that this distress signal is coming from a beacon nearby. The distress signal is not detected by any sensor, but the distress beacon must have X and Y coordinates, each no lower than 0 and no larger than 4 million. To isolate the distress beacon signal, you need to determine its tuning frequency, which can be found by multiplying its X coordinate by 4 million and then adding its Y coordinate. Okay. In the example above, the search space is smaller. Instead, the X and Y coordinates can each be at most 20. With this reduced search area, there's only a single position that could have a beacon. X equals 14 and Y equals 11. The tuning frequency for this distress beacon is that. Find the only possible position for the distress beacon. What is its tuning frequency? Okay. So walking through all 4 million squared possibilities seems like a bad idea. Because 4 million squared is, 1.6 times 10 to the 17th or something, 10 to the 13th, I don't know, some 10 to the number in the teens that feels like it's going to take a while. So let's probably not do that. So interestingly, though, how did we manage to get beacon nearby? The distress beacon is not detected by a sensor. The distress beacon must have X and Y coordinates each no lower. But we just looked at 2 million. And there were 26 positions. But the answer... Okay, the answer was a big number that was bigger than 4 million. So that's logical. Trying to think what the efficient way to do this is going to be. So, in general, with these sorts of algorithms, the thing you're looking for is like how you can be lazy and not calculate things either multiple times or not calculate things at all. Sorry, I didn't have my screen share up. Anyway, this is the puzzle. So, certainly we're going to have overlap in our different beacons search areas, which feels like it should allow us to quicken the search. But we're kind of already dealing with that by using like filters, or I guess the all predicate is going to exit as soon, or the any predicate is going to exit as soon as it finds even one. So that's kind of already being handled. The other thing that's going to be true is that the number of, like, we should be able to search the space in a somewhat intelligent way by starting far away from as many of them as possible. There are also circles with respect to L1 norms. Trying to think, can we order? We can't really order the sensors relative to a given position, because I guess we could order the sensors. One thing that would help is ordering the sensors in decreasing order by how far they are from their beacon, because then you're gonna have the biggest radius sensors, which are gonna hit the most things earlier in the queue, and they're gonna eliminate more. They're gonna eliminate faster, and you're never gonna have to check the bottom ones. Maybe we start with that. Maybe start with something like that. and Wizard says, Mizzard X says, my solution takes several seconds in debug mode. In release mode, it takes slightly below 1 second. Yeah, I think I assume I'm on debug mode because I haven't messed with my environment lately. But I feel like there should be something more efficient than just cramming through all of these points. So anyway, I'm not going to be able to solve it in the next 15 minutes, which is how long I would have. So I think I'm going to call it here for the day, and I'll be back maybe tomorrow, certainly on Thursday, if not at 1 p.m. EST. Yeah, hope everybody's having a good one. Mizzard, thanks for stopping by. If you haven't already, please follow. I appreciate it. Helps me out. And yeah, have a good one.